Hi there, in this video we're going to walk through a logistic regression analysis in SPSS. You can follow along with the logistic regression example in SPSS here. Here's the example data set I'm going to be using, and here's an example of the write-up. So if you want to follow along, you can see here here's my notes how you conduct logistic regression analysis in SPSS and annotated output. You can also find the example results section on SPSS, on Canvas as well. So in this example, we're interested in examining the variables that predict whether students will qualify for an honors composition course. And so we have data on 200 high school students that include whether they qualified for the honors composition course. And so this is coded coded 0 for no and 1 for yes. So if this variable is the honors comp variable is 1, then the student did qualify for honors composition. We also have a measure of the student's family's social economic status, and this is a categorical variable coded 1 for low, 2 for medium, and 3 for high. And we also have scores on 2 separate standardized tests, a standardized measure of their reading ability and a standardized measure of science achievement. So in this example, we're going to regress honors composition on social economic status and reading and science scores. So the example data set, Logit EX, is saved on Canvas. Right here, you can download it and walk through the example with me. So let's pull up SPSS here. Here's here's our example data set. So you can see the honors composition variable is coded 0 for no, 1 for yes. Our SES variable is coded 1 for low, 2 for medium, and 3 for high. You can see how we would enter the data into SPSS. For SES, you're just person 1 is in the low SES group. They have a 34 for their reading score, 39 for their science score, and they're not in the honors composition class. You can see person 3 has a low SES. They have a 63 for their reading score, 63 for their science score, and they are in the honors composition course. We could just run some descriptive statistics on our variables if we were interested. We can see see the proportion who are in honors composition and the average reading and science scores. So you can kind of get an idea of how these scores range. The average reading and science score was about 50. Their standard deviations are both about 10. And roughly 27% of our sample are in the honors composition course. So to run the logistic regression analysis, we click on Analyze, Regression, and Binary Logistic because we have a binary variable. We'll move our dependent variable over here to the dependent side, so honors comp, dependent, and move all of our independent variables over here to the covariates box. And then since we have a categorical variable, we'll just tell SPSS that SES here is categorical. And then we indicate what kind of how we want to treat the categorical variable. Indicator means that we want it dummy coded, and we could choose either the last or the first category to be our reference category. I believe in the example, I picked the last category, so the high SES group, which we're going to compare the other two groups to. So we would, if we change this to first or last, you'd hit change and then continue. We're going to save out the predicted probabilities from the model, and we're going to use this as an indication of as another pseudo r squared measure, so we can get those out of the model. We can click on, if you want like a visual classification plot, you can click here, the Hollingsworth-Leamshauer goodness of fit test. You can click on here, you can get confidence intervals for your odds ratios. You could also click on iteration history here. If you look in the notes, that's one way that you can calculate another one of these pseudo R squares by hand, which will need that. The iteration history here, we'll just click on it. You can get it as well. I don't believe we need anything else, so we'll hit OK. And we'll run the regression model. So the first thing it prints out is just kind of summary information. It talks about sort of missing data. There were 200 participants, individuals included in our analysis. There was no missing data. So the second part kind of tells you how your original variable is coded and how it's internally coded. So SPSS is going to predict values, how it's internally coded as 1. So you might want to make sure, like I want to predict, the odds that students are in the honors composition. So we want to make sure that that corresponds to their internal value of 1. If you had these coded like 1, 2 or something, you just want to make sure that the internal coding of 0, 1 matched what you wanted here as well. If not, then you're going to have to recode your dependent variable. If you have categorical variables in your model, this table indicates how the categorical variables are coded. So we set the high SES group as our reference value. So here it's just doing the dummy coding or indicator coding for you. You can see where it's going to say SES parentheses 1 in our coefficients table. That's corresponding here to the low SES group. Where it says SES parentheses 2, that's corresponding to the middle SES group. It's not this 1 and 2. It just so happens in our case that it corresponds to our 1 and 2, but that won't always happen. If we would have coded the high group, the low group as our reference group, this would be 1 and this would be 2. This would be SES1, this would be SES2. So this is a good way to make so you know how the SES variable is coded in the output below. Block 1, so this just gives your iteration history. You could use this log likelihood, or since it's actually -2 times log likelihood, so it's also referred to as a deviant statistic. You could take the ratio of this deviance in block 0 and the one in block 1 to calculate that McFadden's R square that I talk about in the notes. Basically what to know about block 0 is this is your null model. This is the logistic regression model that it doesn't include any of your predictor variables. Basically, you're saying, look at this last one. We're saying let's just assume that everybody's not in honors composition. How well do we do at classifying folks? And you'll see that we classify about 73.5%, around 74% of people correctly by just guessing that everybody's not in honors composition. So this is our base model. We want to see if we can improve on this by adding in additional predictor variables. And so that's what we're doing here in block 1. Here's our iteration history for that block. Here was the -2 log likelihood here. This is where I calculated in that McFadden's R square in the notes. You can calculate it as the ratio, so the deviant statistic or the log likelihood from block 0 and block 1 minus that ratio. this omnibus test of model coefficients. So this is basically a likelihood ratio test, and it's basically saying that like our independent variables as a set, are they doing a good job of predicting whether someone is in honors composition, kind of above and beyond what that null model is doing. And so we want to see that, yes, our model is doing, is doing a good job of predicting, at least doing a better, sorry, I should say it's doing a better job of predicting uh, kind of membership in that honors composition course compared to our null model. If you were to do this as like a block entry or a sequential kind of regression like we talked about in OLS, you could do the same thing here. You could enter your independent variables into blocks. You could get a one of these likelihood ratio tests for each one of the blocks, comparing block 1 to block 2, block 2 to block 3. Here, since we entered all the variables kind of simultaneously, we're only comparing them against the null model. This next table here gives us our pseudo R-squared values. So SPSS reports 2 different pseudo R-square values, and I'll show you a little later on how you can calculate a third one. There is no direct equivalent to R-square as it was, I guess R-square as in the proportion of variance explained in our outcome, proportion of variance explained by our independent variables in our outcome. There's not a direct equivalent to R-squared in logistic regression. But there are several different, what they call pseudo R-squares, just different ways of getting at that variance. Explain, you see that each way that you calculate it, you get a slightly different estimate. So basically what I do is just report all of them, and then you can kind of get and give your reader sort of all the information that you have. SPSS reports these two, Cox and Snell. I'm not really sure how to say this. Nagartke, I'm going to butcher it. R-square value. Basically, the second one is a correction to Cox and Snell. The Cox and Snell has a limitation that the maximum value cannot be 1. It's basically a correction to that McFadden's R-square. Show you how to calculate in the notes. It's a correction for sample size, but then it has a limitation that its maximum value isn't 1. And so the second one sort of makes an adjustment to Cox and Snell, but then it's been shown to be like an over estimate of what the variance explained might be. So a lot of times I just report both of them in an analysis because they're trying to give you an estimate, sort of what that variance explained might be. The Holmesmer-Lenshow test is kind of a sort of a goodness of fit test. It's, how well does this model fit my data? And this is one of those cases where we want to fail to reject the null hypothesis because it says that our model fit our data well. Sometimes, especially with a large sample size, sometimes you'll see this test be statistically significant. I wouldn't just completely throw away my model in that case. I would look at this contingency table down here and try to kind of diagnose that area of misfit. This is if the model's doing a good job of predicting who's in which category, then as we're in these lower deciles, we would hope to have do a better job of predicting that you're not in the honors composition, where when we get into the upper deciles, we're doing a better job of predicting that you are in the honors composition. And so you would compare basically the observed to the expected frequency. And so you can see all of ours are pretty close. That's why we're failing to reject this, this chi-square test. But if it was significant, you'd kind of look at the areas where there was misfit and just kind of see how bad it's actually doing. Here's another indication of of goodness of fit. It's this classification table. Here it's how well is our full logistic regression model doing, predicting whether you were in honors composition or not. You can see overall we're correctly classified in around 80% of cases, which is probably pretty good. It's an improvement over the null model where we're only classified in around 74%. You can see we do a much better job of classifying people who are not in honors composition than we do at classifying people who are in honors composition, right? We're only, those who aren't honors composition, we're only, correctly classifying around 51% of those people. This is your coefficients table. You can see we have our unstandardized coefficient, standard error. Our wall test is sort of like our the t-test in OLS regression. Then sig here is again our p-values. EXPB here. These are our odd ratios. We're exponentiating the unstandardized coefficient. That's why it's written this way. So these are our odd ratios, and then here's our confidence interval on our odds ratios. So if you look at the notes on Canvas, or rather the example here, you can use this table to write out the regression equation, and so that's what I've done here. You can see you can take the constant plus your unstandardized coefficient for each one of your terms times that coefficient, 0.098 times reading plus 0.066 times science, yada yada yada, and you can get your regression equation if you need to calculate that. Remember, this is your remember the regression equation is in log odds. So how do we interpret then our coefficient estimates? We'll go back to our actual output. I just wanted to point that out. So I mainly use these unstandardized coefficients here to kind of just give me the direction of and whether there is a relationship with our dependent variable or not. So we could look at reading score here. We can see that it is positively related with whether or not the student's in honors composition or not. Same thing with science achievement score. We can also see that social economic status 2 here. So this was whether you're in the medium social SES group compared to the high SES group is negatively related with whether you're in the honors composition group. Since it's negative, what it's saying is the references, or it's pointing towards the high SES group, is saying that they are more likely to be in honors composition than someone who is in the medium SES group. So remember, the thing to remember here is that these coefficient estimates are on a logit scale. So, it's saying that a 1 unit increase in reading achievement corresponds to a 0.098 unit increase in the log odds of being in an honors composition course. So usually interpreting log odds units isn't very intuitive, so we'll exponentiate the coefficients and convert them into an odds ratio. So an odds ratio is a ratio of odds, so this is a ratio of odds for the thing and the odds against it. Right, so odds ratios of 1 indicate no relationship. Odds ratio greater than 1 indicate a positive relationship, and odds ratios less than 1 indicate a negative relationship. So odds ratios greater than 1, I think, are a lot easier to interpret. So if we look at like the reading score here, so this is saying that for every 1 unit increase in reading would correspond to around a 10% increase in the odds of being in the honors composition course. And I get that from, these first 2 decimal places behind the 1. That's where it's corresponding to a 10% increase. A 1 unit increase in science achievement score corresponds to about a 6.8% or a 7% increase in the odds of being in the honors composition course. We see here that low SES compared to high SES was not statistically significant, but here we see that those in the medium SES group compared to those in the high SES group, it was statistically significant, and now the odds ratio is less than 1. So we can do 2 things. So we can subtract this value from 1. So what do we get? 1 minus 0.363. So that's saying going from the high SES group to the medium SES group would correspond in a 64% decrease in the odds of being in the honors composition course. Another thing you can do is you can take the inverse of the odds ratio, so 1 divided by 0.363, and we get 2.75. So we take the inverse of the odds ratio, and then we would flip the comparison groups. So it's saying that those in the high SES group have almost or more than 3 times as likely to be in the honors composition group than those in the medium SES group. So the inverse odds ratios work well when you have a categorical variable where you can take the inverse of the odds ratio and then flip the reference groups around. You could also interpret then you can also talk about the confidence intervals as well on each of those. You can also calculate some predicted probabilities for a strategically or some hypothetical case that you think is important. And so that's what I did here. Basically, you solve this regression equation for some hypothetical case. So say we wanted to compare, I think in my example here, I compared someone who has, what's the probability of an honors composition with someone who has like average reading, has an average reading score, versus somebody who has a reading score 1 standard deviation above the mean. So the average reading score is around 50 with a standard deviation of 10. So I'd fill out this equation replacing 50 here in one case and 60 here in another case. And then I'm just going to keep all these other values the same. So I'm going to say they have average science and they're in the medium SES group. And so that's what I did here. You see, so this would be the logit for someone who has average reading, average science, and who is in the medium SES group. So their low SES would be 0, their medium would be 1. This would be their logit estimate. We can convert then the logit into a predicted probability using this formula. And I'll show you how to derive this in the notes here. Notice we flip the sign on our logit, so that's why it's positive here. So someone who has an average reading score, average science score, and who is in the medium SES group has about an 8, has a point, their predicted probability of being in the honors composition course is 0.08. So they have like an 8% chance or 8% probability of being in the honors composition group according to our model. So someone who has, let's say, a high reading score, say 1 standard deviation greater than the mean, we plug in 60 here for theirs. The reading score is still 50. They're still in the average or middle SES group, medium SES group. We calculate their logit and then change that into a predicted probability. So we get 20%. So someone who has a reading score of 1 standard deviation above the mean, but an average science score and a medium SES has a 20% probability of being an honors comp. So you could really do this as just an example. You could do this for any hypothetical or strategically important case in your model. So that was just one example of how you would go about doing that. This classification table is really just a visual representation of this classification table. So it's kind of showing you how well your model predicts. What you're wanting to see, you're going to want to see a bunch of Y's over here on this side above the 0.5. See where it's all turning into Y, saying that they're, here's somebody who was not in honors comp, but we're predicting that they are in honors comp. Same thing over here. Here's a few people who are in honors composition, but our model's predicting that they're not in honors composition. So we could try to figure out maybe what's going on with these cases. When we ran the model, we asked it to save out the predicted probabilities from the model. So this would be the predicted probability for someone who was in the low SES group, who had a reading score of 34, a science score of 35. This would be their predicted probability. There's only maybe a 3% chance they were in honors comp, so our model would predict that they're not. Anybody greater than 0.5 is going to say their predicted probability who's greater than 0.5 is going to say yes, they're in honors comp. So like this person, we would say yes, they're in honors composition. This one they're not because it's less than 0.5. So what we could do is we could actually just correlate these two variables and square the correlation. So here's their predicted value, here's their actual value, and then we could correlate these two variables and square the correlation. That's where the term R squared comes from in LLS regression. So it'd be another indication of the proportion of variance explained. So you could either run a correlation between them and just square that term yourself. I'm just going to run it as a logistic regression model, putting the predicted scores as the dependent, the actual scores as the independent variable, just saying okay, and then looking at the R squared of that model. So it's saying, so that's just another indication of the proportion of variance explained, and just another pseudo R squared value that you can interpret in your model as well. As always, if you have questions or concerns, shoot me an email. Everything should be explained in the write-up here as well. Try to annotate it as best as I could. If you have any questions, let me know. Thank you.